Thank you, Ron. Clicker's up there. That's great. Thank you. I have to say that I am honored to have the time to speak to you this morning. And I would first like to say that I'm very proud of what the team at Wachovia has done over the past year. We've got a very amazing team of people at Wachovia, which is part of the reason why I went to Wachovia and why I left IBM was because of the talent that Tony Bishop and Mark Cates and Susan Sertoma, our CIO, had assembled. And I'm honored to get to work with these bright minds every day. And I just would like to acknowledge those guys and girls and thank them for what they've done, because we've had amazing success, and I'm really proud of where we've gone in the last year at Wachovia. So if we could just put my slides up. Okay, great. So yesterday on my way here, I was coming in from Charlotte, North Carolina, where Wachovia is based. By the way, Wachovia is traded on the New York Stock Exchange, ticker WB. You should add that to your 401k, because we're going places. Ken Thompson's a great leader. And so as I'm traveling here yesterday, and I flew through Salt Lake City, and I got to spend an extra 5 hours in Salt Lake City thanks to Delta. And I got to reflect on Judge Kimball's ruling on October 10th, because he's based in Utah. And I'm pretty happy, and I'm sure you guys are also happy, that Judge Kimball found us all innocent for using Linux. And he told Darrell McBride that he can either innovate to make profit or just go away. and that's where we are today. So evidently, Novell did us all a favor back in 1995 when they figured out how to sell SCO Unix code without actually selling them the copyright. And that was essentially the result of the trial, was that McBride's argument was actually moot. So I think that's a big win for the Linux users in the crowd there, and I'm just happy that he's not going to sue us for using his Unix code. Allegedly, there was Unix code in Linux. But this open source stuff, it's tricky business. Open source is, the legality of open source is tricky business, especially for a bank like Wachovia. We spent a lot of time trying to make sure that when we do use open source, that we're going to get support is really the first question. So yes, we do use Windows. Yes, we also use Linux. Yes, we use JBoss. Yes, we use WebLogic. A bank like Wachovia, especially since we do so many acquisitions, we're never going to have one big homogeneous environment, and there will always be bits of open source and bits of COTS products in our environment. We're here talking about virtualization today and infrastructure management. You guys are probably all VMware aware, or users of VMware. And that recent IPO from VMware, or from EMC, to sell 13% of VMware for about $957 million, that was certainly an interesting sale. That's the marketplace saying that virtualization, at least they think VMware is worth about $7 billion if we paid $957 million for just 13% of it. Pretty interesting, given that VMware and virtualization is supposed to save money. That's pretty big spend on software. So someone's figured something out. As a corporation like Wachovia, we're nervous about it because we're worried that virtualization is simply shifting costs away from the operating system vendors and towards another vendor. So we have to manage this spend wisely. I'm also interested in what Citrix is doing with ZenSource. You guys have probably heard about the ZenSource acquisition, where Citrix spent about $500 million on ZenSource, about a $100 million company. That's interesting, especially since about $100 million of that's going to go to make sure that they don't lose the talent at ZenSource. You have to think about all these things. What are they going to do with this technology? How is this going to change the landscape? What is the future of Windows and Windows Server and Linux in the data center? If hypervisors really are all that you need to run your application logic. BEA is doing some interesting things where they're now announcing support to run BEA directly on a hypervisor without the need for an OS. That's interesting stuff. That's going to change the way we build our servers in the future, assuming this is where we all choose to go. So what am I going to talk to you about today? I'm not going to spend a whole lot of time talking about virtualization as a way to consolidate servers. That's not really our focus. Wachovia is an interesting company, and I think Papadopoulos over at Sun, he's a pretty smart guy. He had it right, or at least recently. He was mentioning that IT companies and organizations like Wachovia Investment Bank are what he calls redshift companies. And he compares us to an object in outer space moving away from the observer so fast that the wavelength of light begins to lengthen, and the light starts to turn red. So he's making the analogy that we need more computing power than Moore's law can keep up with. You know, Moore's law states that the number of transistors on a chip will double every 2 years. So he's making a statement that redshift companies are growing faster than IT can keep up with. In other words, we need more compute power than the industry can give us. And so that's why you see our data centers growing. Well, that's interesting. I would definitely say that we need lots of computing power, but you also have to wonder about, well, what about all the underutilized compute capacity? Maybe we are being inefficient. So it's not one or the other, it's both. We are inefficient in our use of technology, but we also need a lot more technology. Our compute requirements for analytical analysis is growing very rapidly. So I'm going to talk about our use of grid computing and our use of technology and our use of virtualization, not simply to reduce costs and to create efficiency, but I'm also going to focus on the value that technology provides. You have to ask the question, well, why is a company like Wachovia or Citibank or all these other large corporations, why are they spending billions of dollars on technology? They have to. When the computers go down, when the infrastructure goes down, we lose money. We only make money. We can only think about the new currency. The new currency isn't a coin or a dollar. A photon and an electron today is currency. Money is moving over wires. And if those bits don't travel over those wires, then that transaction cannot occur. We lose money. We can't make that trade. We can't look at the market data. Technology is core to a bank. That's why I like working at Wachovia, because I feel like I'm providing direct value to Wachovia's bottom line by creating solutions that provide Ken and his people what he needs to run the business. Oh, I need the slides up. So I'm going to talk about SOA and infrastructure virtualization, how they relate. I'm going to talk about what Wachovia's real-time infrastructure looks like. I'm going to walk through the methodology that we executed to get here over the last 5-6 years. And then I'll wrap it up with a comparison of where we would be if we stuck with traditional IT versus a services-oriented infrastructure. So at Wachovia, time to market really is our top priority. Efficiency is also important, but I would say it's secondary. And so because time to market is important, we spend a lot of time figuring out how to reduce time from the equation. And when I say reduce time from the equation, I mean development time, test time, moving boxes into production. I'm not just talking about the time it takes to install an operating system on a server. I'm talking about the end-to-end life cycle from this trader has an idea on a new product that he wants to figure out how to price, and he has to get that algorithm on a server, and he has to integrate market data with that server in order to figure out how much this new financial product should be sold for. That's development, that's testing, that's moving products or moving solutions into production, and it's creating a resilient solution where there's failover to a DR site. How long is that timeline, right? In some cases, we can do that in 3 months. In some cases, depending on the complexity of the system, it could be a year, it could be 18 months. We need to shorten this end-to-end timeline, this life cycle of innovation, of business model, of business process innovation, of using technology to transform a business process. That's the time I'm concerned about. That's what I mean by time to market. George Orwell, I quote George Orwell up there, he reminds me of what we do with market data and how we analyze market data. He made a statement once, actually back in 1948 when he wrote 1984, that if you control the present, then you control the past and the future. You're essentially creating the future when you control the present. Being able to analyze what's happening right now and make an intelligent decision in real time, that's what we mean when I say real time. It's taking high amounts of market data and analyzing them in real time. And as you can tell, I get kind of excited when I think about this. This is really the convergence of networking, of servers, of software, in one massive business application. And if I get too excited and I lose you, if I go too deep, just raise your hand and say, hey, Ryan, wait a minute, slow down, because you're off on a tangent. Essentially, why are we moving so fast at Wachovia? Well, the business needs us, they're watching us, and it's time for us to execute. So how does SOA and infrastructure virtualization relate? Well, essentially, in order to get faster time to market, we have to break down the stovepipes in silos. It takes too long to get a front office application or middle office application to integrate with a back-end GL, the books and records system. And we have many systems across the organization, from capital markets, from international trade, to treasury services, to managing our risk. We have to do this faster. We have to get these systems talking to one another quicker. We want to build composite applications, what SOA calls a dynamic application, taking reusable components and code and services running in the data center, rapidly assembling them and creating something new. Flexibility is very important to us. We want to be able to roll in innovations from technology companies like Intel and Dell and IBM and Sun and all these vendors and Cisco. We want to roll those changes in, that new innovation, into the solution without taking down the business. We don't want any downtime. So we want transparent infrastructure change. We want to continuously evolve and adapt. And then lastly, it needs to be simple to manage. There's the catch. All right? If there is a problem, we need to be able to identify the problem and remediate it as quick as possible. So think about engineering. The simplest design, look at what Apple is doing with iPods. Simple is beautiful. Simple is perfect. Make it simple. The industry has acknowledged what Wachovia has done. Since 2004, Wachovia has been playing with grid computing. Wachovia was one of the original investors in Data Synapse, and we now have a huge Data Synapse grid that is about 3,000 servers large and 7,000 development desktops large. What did we do? We built an infrastructure to support, primarily, I'm focused on corporate investment bank. I'm not doing ATMs and checking accounts, although I do partner with that side of the retail bank. But primarily, my focus in CIB is on corporate investment banking. And so you see on the top of the chart, and I'll go into the bottom of the chart in a bit, the top of the chart shows the business functions who demand IT, who need IT to run their business, and who we're supporting. We support the sales desks, we support the analytics desks, we do customer insight. 3 major business lines: global capital markets, George Vega's world, and he's essentially the divisional information officer for global capital markets, kind of like a CIO. And then treasury finance and analytics, and then the international business where we do IFTs, international funds transfers, for our clients overseas. And we give them good rates by integrating that with our foreign exchange business in global capital markets. And so we can get a really good rate on a currency. And that's where, like, think about what an ESB does. Being able to take a technology like the foreign exchange technology, the FX technology on the far left-hand side of the chart, and integrate that with the global trade funds transfer business application on the right-hand side of the chart. Completely separate business lines, but they need to talk to one another. They need to integrate. That's where the concept of an ESB provides a whole lot of value. So what is the ROI of SOA? The bottom bar on this chart, the yellow line, shows the SOA spend, your new project to ramp up an SOA initiative. What did we do in CIB? We formed a team. I'm a leader of a team of really smart people. They're developers, they're infrastructure people, they're networking people. People cost money. This project costs money. So that's the yellow line. The time and effort it takes to build something that is mass customized and reusable. The pink line is status quo, maintenance of IT. So what the chart is showing is that if you invest in SOA and you really execute SOA and you start mandating reuse of SOA components and shared services, you will see that traditional IT spend start to decrease over time, because you're not reinventing the wheel. You're not continuing the madness to continue to build duplicate technologies and different business lines. When you start leveraging that economy of scale, where you build something once and you reuse it many times, now you're doing what Sun had in mind when they invented Java. Write once, test everywhere. Build it once, reuse everywhere. So how did we do it? First thing we did, when I say we, I mean our leader, Susan Sertoma. She's our CIO. What she did was she organized her teams, her technology people, to be directly aligned with the divisions in CIB that she's supporting, like global capital markets, like foreign exchange, like structured products, like vertical mortgage integration, like the international trade business, like treasury services. And those teams all depend on our group, the CTO group, at the bottom of the chart. The CTO group provides shared services, a large development grid, a J2EE runtime environment, a .NET runtime environment, a .NET desktop for these people to build their applications on top of. That means that these business lines, these IT teams, yes, they're directly aligned with the business, and so they can build solutions that are valuable to those business lines. However, they're also reusing shared components. That's paramount. You have to have this kind of organizational structure in place. Otherwise, you're going to have, and you still have it, NIH. And NIH is probably the biggest inhibitor, in my opinion, to SOA being real. NIH, if you haven't heard that acronym, is not invented here. So watch out for NIH. And partner with these other development people and these other development teams in the organization, because you need to create a solution that is both your solution and their solution. So there isn't that, oh, this isn't mine, I don't trust it. You have to have trust. Trust is the fabric of all economics. Supply and demand for products in the marketplace and supply and demand for what we're building in the SOA shop and what they're reusing. You have to have that trust. We want in Wachovia, we want to attain a state of transistasis. This is a biological term that's the antonym of homeostasis, which means transistasis means to constantly change, to constantly adapt, collect feedback from the environment, and to adapt, to use that feedback and to adapt accordingly. Natural selection in life prefers not the strongest or the fastest, but prefers the fastest to adapt to change. Temperature drops 50 degrees, you better grow some fur. All right, that's what transistasis is. So how do we do transistasis in business? Well, we have this feedback and adapt loop of development, where we have quarterly checkpoints with the business leaders and bi-monthly checkpoints with the development leaders in each of those IT organizations. And we make sure that what we're building is directly aligned to what they need. And we track all of these requirements and all of these solution designs in a requirements management system. And we make sure that we test in accordance to their needs. We're not esoteric and inventing in a vacuum. There has to be, like I said, trust. There has to be communication. You have to have a requirements loop that feeds directly into the development cycle. And be iterative in your approach. That's why I show the tornado. Cross the chasm and then reach the tornado of innovation and continue that iterative loop. Don't fall into the waterfall trap where you take on this 1-year-long development life cycle. You try to get all the requirements figured out, all the use cases figured out over 3 months, and then you start building something. Take on 20% of your requirements and build 20% of the solution. And then when you know what the rest of the requirements are, the business has figured it out, continue the rest of the project. Iterate, 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 iterate. Move away from a year-long project towards a 2-week project. That way you know, well, you show you're providing value, you have constant deliverables, you're getting solutions into the hands of the developers, and then they're giving you honest feedback, and you're able to take that feedback and improve the solution to meet their needs. So what did we build? What were these reusable components that we built? Yes, we have at the bottom of the chart a virtualized runtime environment, but that's only the beginning. The reason why we're still actively busy and we still have lots of development activity going on in CIB and Wachovia is because virtualization is not the end, it's just the beginning. You then have to take it to the next level and build components on top of the virtualized runtime environment that provide value to the business line. You want to, again, like I said at the beginning, take the end-to-end life cycle of development down from months to weeks if you can. That's what composite application development is all about. It's about reducing the development life cycle and shortening the test life cycle by using components that have already been built and tested and tuned for performance, designed for scalability and resiliency, and are ready to go live. If you start from scratch, you have to do all that over again, and that's time. And time is money, and time is also probably an opportunity lost. So what did we build? We have an Axis framework where we have a .NET desktop environment to build fat client applications that you deploy to a desktop, a trader desktop. High-speed feeds from market data sources go into that fat client. We've also got a rich internet application environment where we do things like Ajax and Adobe's Flex technology. You should check out Flex, it's pretty interesting stuff. The mediation framework, that's where we do our authentication, authorization, audit logging. We do our messaging integration, our ESB gateway. We're moving towards appliance-based ESB gateways and XML firewalls, and we're doing XSLT transformation from one XML format into another XML format to get out of the business of writing code to change a CSV file into an XML file and wrap it with SOAP. We're exposing TIBCO queues and MQ queues and ODBC calls as web services, wrapping all these integration destinations as web services. We have integration to our grid through this ESB gateway. You can run any Java code or any C code or C++ code on a grid of computers and expose that code, wrap it as a web service. Data Synapse does that out of the box. You deploy anything to the Data Synapse grid, he exposes that code as a WSDL for you. And then you just point your ESB gateway to the WSDL, authenticate the user's authorized to use 100 servers or 1,000 servers or 10 hours of time or 2 days worth of time, whatever the job is. You don't just want to leave that wide open. You have a grid of machines, you got to lock that down. So security is paramount for grid and virtualization. I mean, I'll talk about security in a minute. And then we decided, well, you can't just have one type of server. It doesn't make a whole lot of sense to have one type of server. There are different use cases. You have to design, build purpose-built solutions. All right, so we have a basic application server. You want to write a POJO, plain old Java object? Okay, run it in that J2EE container there. But if you have latency-sensitive requirements, you're taking high-speed market data feeds in, that's a different breed of solution. Same thing with if you need ACID transaction support. You want to maintain the state of a transaction over a day, a week, or a month. You want to do workflow on that. Completely different requirements than latency-sensitive requirements. Same thing, analytical processing or grid utility. Number crunching, going back to Papadopoulos, that's expensive. That requires huge amounts of compute resources. You're talking many quad-core, multi-core servers aggregated together. Virtualization isn't just about carving up one big box into many little boxes. Virtualization also includes taking many commodity boxes and aggregating them together and abstracting the fact that they are many little boxes, that it is a grid. That's also virtualization. And we spend a lot of time with the analytical side of virtualization in CIB because we're crunching numbers to calculate our VAR nightly. The VAR is for Basel II. It's the value at risk. This is how much money a bank can lose at any given moment with the outstanding debts or bets that we have. So we have to keep that amount of cash on hand to comply with Basel II. So we calculate this nightly. You have to take in market data, and you have to take in our books and records, and you run that job. And that's extremely taxing from a CPU perspective. In the past, it's taken us 17 hours to calculate the VAR. We just deployed a very dense rack of servers, 240 cores, 8 gig FBDIMMs on each machine, and we got that job down to 30 minutes. And it wasn't just the cores and the FBDIMMs. FBDIMMs are pretty cool, and multi-core CPUs are pretty cool. But in order to do this, the big challenge with grid and the big challenge with underutilized resources is the fact that I/O wait is the CPU time killer. When the grid is sitting there waiting for the data to come out of the database or over the wire, that's your number one challenge. And so the way we attack that challenge is we use a level 2 cache. And we stage the data into a memory space. So the reason we have those FBDIMMs in there, they're high-speed DIMMs. The reason we put those FBDIMMs in there is because all the data that grid job needs when it runs at 2 a.m. is already preloaded into memory, running in a Java cache. And we just make a Java call to this distributed Java cache instead of going all the way out to a database, to an ODBC database, to a Sybase database, to an Oracle database. Instead, all that data is running right there on the exact same machines where the CPUs are that are going to crunch the data. By putting all the data on the same physical machines, connected to the same switch, in one rack, running in memory, you go from maybe a gigabyte of data per minute to 20s of gigabytes of data. Well, actually, I'd say closer to 6 gigabytes of data per second. To be specific, on a 1 gigabit per second network using a technology like coherence, it used to be called Tangasol, Oracle bought them. Coherence will give you about 98 megabytes per second of throughput. And it scales linearly. You add more JVMs, you get more performance. This is how we attack the problem of I/O wait and latency from database calls and JDBC calls and ODBC calls. That's your biggest challenge. So look at caching technologies. There are plenty of caching technologies in the marketplace. We like coherence. We think that it's a best-of-breed technology, and you should check it out. Cameron Purdy, you're welcome. A real-time infrastructure has shared, virtualized, and dedicated resources. In other words, it's not just about carving up big boxes into little VMs. Yes, you can create a grid. You can use Data Synapse to create a grid that's made up solely of VMs, of virtual machines. You can also aggregate VMs running Linux and Windows with dedicated machines. So that's what I mean when I say that a real-time infrastructure needs to take into consideration all of the components that your company has invested in. Leverage your existing investments. That's my message. It's not just about consolidating. Yes, consolidate where you can, where it makes sense. For your low, non-mission critical applications, email servers, stuff like that, file servers, web servers that do corporate intranet portals, sure, consolidate that stuff. But if it's a trading application or it's a mission critical application where money's on the line, you're probably not going to want to carve that up. You're probably going to want to give it a dedicated machine, probably many dedicated machines. So that's why I say, yes, pull in virtual machines where you can. We use virtual machines in Wachovia for low priority applications. We use them in the Innovation Factory lab. All of the development work is done on VMs, and then we promote it to dedicated machines after we go through the development and test cycle. The technology like Data Synapse provides a very valuable service to us. We're not focused on the business of provisioning and orchestration and service level management and monitoring of all the resources. If a machine goes down, how to route the job to another machine. We use, I guess it's called griddleware. It's like middleware, but it's for a large distributed grid. And so Data Synapse is a form of middleware that takes care of all that logic, where it keeps tabs on the life and the performance of the resources that are running in your data center. And there are other technologies that compete with Data Synapse in the marketplace. Choose the one that's right for you. Platform computing is out there. Globus is out there. Globus is the open source alternative. I personally like Data Synapse. Data Synapse is getting into a new space right now called Fabric Server. And that's where it's not just about a grid for unmanaged C code and C++ code, but Fabric Server is actually taking advantage of the APIs that vendors like WebSphere and BEA WebLogic and JBoss give anyone. They're using that API to add additional servers to a cluster of container-based application servers and adding more servers to those J2EE clusters on demand. They're also managing environments like Documentum and Cognos. That's pretty interesting to have one infrastructure management technology that can add resources to analytical environments like grids, as well as add resources over to a pool of J2EE containers like WebLogic or JBoss. So that's what Fabric Server is, and it adds resources that are unused. They could be running Windows and need to be re-provisioned with Linux, have JBoss installed on it, have WebLogic installed on it, deploy the EAR file to that container, and now you're up and running. It's now a new member of the cluster. And it does this when CPU utilization on the existing servers in the cluster starts to run hot. Everything's at 75%, response time's getting slow, kick off the policy to add another resource to that cluster. Yes, you can do this with WebSphere directly. WebSphere's got XD. But if you're running more than one environment, if you're an environment like Wachovia where you have a heterogeneous blend of technologies like WebSphere, like WebLogic, like JBoss in one environment, then what are you going to use? You're going to use 20 different infrastructure management tools? No. So Data Synapse is partnering up with another company. You're going to hear tomorrow at 11:30, Kevin from Scalent is going to talk about how they're partnering up with Data Synapse. And Scalent is an interesting way to re-image or repurpose a box to become the identity of another box. And it doesn't do this through software installation. It's actually the converse of software installation. You don't install any software on the hard drive of the server. Instead, you reboot the server and pixie boot it off of another LUN. So it's as fast as a reboot. So what you do with Scalent is you create a bunch of images for servers. You put those images on an image server someplace. You reboot the box, and now it's no longer an Intel Windows box. It's now an Intel Linux box, as fast as a reboot. How long does a reboot take? All right, depending on the box, could be as fast as 60 seconds, could be as slow as 5 minutes. Before you do things like move servers from one VLAN to another VLAN. It was once doing web traffic. It's now doing internal analytics, or it's no longer a JBoss box. It's now a grid box running C code. Before you do stuff like that, you need a security policy solution in place. You can't just reconfigure the Cisco switch. When I talk to the network guys at Wachovia about things like reconfiguring VLANs on switches, they freak out. They go, no, your software's not touching that. Because that's security. That's the trust domain. So think about solutions that abstract the security policy from the physical resources, from the switches, from the servers, from the J2EE containers, from the .NET environment. There's an emerging concept in the security world called XACML. It's the Extensible Access Control Markup Language. It was invented by a team of security vendors out in the marketplace. It's now an OASIS standard. It's part of Web Services Security 2, and it's very related to SAML 2.0. And there are vendors in the marketplace now who are creating XACML solutions. This is a slide courtesy of Shaker, who's the CTO of Securant, a new company based in Mountain View, California. And Securant is a company that has a policy administration point that takes any kind of security policy and lets you define who the user is, what the role of the user is, what resources that role is allowed to use, and what the conditions on that policy are. Sure, he's allowed to execute trades in this trading application for structured products, but how much? What's the limit on the trade? Sure, he can use the application, he can get in, but once he's in, what is he allowed to do? Is it a $5,000 trade? Is it a $1 million trade? What's his budget for the day? Has he exceeded the $10 million cap that this trader has? After the trader has exceeded his $10 million cap, he gets cut off. That's security policy. And today, all these security policies are typically written by developers in that one business line. This is huge time. This is a huge amount of time and complexity. And I think it's also a risk to have many different teams of programmers, many of which are probably offshore programmers, not even real employees of the company, writing security business logic over and over and over again to do things like make sure that when a budget has been exceeded, that no more trades can be executed. This is where I say that security policy and the business rule are actually the exact same thing. And I think you're going to see a shift in business rules in the marketplace start to move towards this, where the business rules engine, like ilog and rules and JRules, starts to converge with XACML security policy enforcement point solutions like Securant. Because you can't divorce the two. A business rule has to, at some point, be turned into a security policy and enforced. So things like a policy administration point, which is a nice friendly web user interface to create security policies that then stores that security policy in an open standards format called XACML, which anything that talks XACML can use. Even a provisioning engine like Scalent and Data Synapse. Even a JBoss server who's executing a POJO or a servlet to do things like execute a trade can all point to this one policy decision point. We use technologies from IBM like DataPower as policy enforcement points. DataPower, the XI50 appliance, can talk XACML. So we're doing things like having our XI50s integrate with XACML policy decision points. And as the web services transaction flows through, essentially it's a web application firewall or web services proxy. As the transaction flows through there, he rips open the SOAP envelope, looks at the SAML token, gets the identity of the individual, looks up the identity of the individual in the policy decision point, and makes a decision. Is user allowed? Yes or no? If no, transaction rejected. Same thing happens. Securant has, if you look at the bottom of the chart, they have policy enforcement points that also run inside your environments. They have PEPs for web services. They have an CG policy enforcement point. They have PEPs for databases. They do things like get in the middle of your database call. So instead of just having an ODBC call directly to Oracle or Sybase or SQL, it flows first through a policy enforcement point piece of code that looks up what you're trying to do, who you are, and says, so say you do select star on accounts, a table. You want to see all the accounts in a table. If you're not authorized to see all the accounts, it returns nothing. That's what a policy enforcement point does at the database layer. So think about these concepts all the way down to your business logic and including the provisioning logic before you start moving servers from one VLAN to another VLAN and reconfiguring the switch. Make sure that not only is the security policy propagated as these changes are made, but that when that large server, or maybe those 100 servers, are requested to be moved over during a change window on Saturday night, when someone says, I want to move those 100 servers from this analytical pool that's used for calculating Wachovia VAR over to this other application to do load testing, that's rejected. Because the security policy says, those servers aren't available for load testing. That's mission critical equipment. Sure, it's idle all day long, but at 2 a.m., they're busy. Don't touch them. That's security policy. So what is a real-time infrastructure? A real-time infrastructure is an infrastructure that is designed for real-time scalability and performance. The chart I'm showing on the screen is real data. You can go to Wachovia.com and look at the trend for the volatility index of the Dow between July and September. This is what I'm showing you, the volatility index for the Dow Jones Industrial Average. On July 19th, which let me just point it out here, right about there, that was the volatility index, relatively low. That was when the Dow hit an all-time high of 14,041 cents. A month later, on August 16th, it dropped 11%, and the market went crazy. When things like that happen, when the Dow drops 11%, that's when money is made and money is lost. A huge amount of money can be made and a huge amount of money can be lost. The challenge for a bank like Wachovia, for anyone who's trying to process market data when volatility gets to be that crazy, is that is a huge amount of data. Look at the numbers I have on the screen here. Fixed messages for trade executions, approximately 20,000 messages in a single second average. Never mind when things get crazy and volatility goes way up. The average is about 20,000 messages per second. Options pricing data, 450,000 messages per second, and estimates say that that's going to grow to about 900,000 by next year. This time next year, options data will grow to about 900,000. The reason for this is the inverted yield curve. Long-term, 30-year-long investments are no longer as profitable as short-term investments, which means more transactions are executed in the span of 1 month. That's volatility. People are making more deals happen in shorter periods of time. Because of all the deals that are happening and all the market activity, that's more data. We want to know who's buying and selling what. Supply and demand. If there's no longer demand for something, that's probably time to bail out. Maybe. So that's what we do. We analyze amazing amounts of market data. A single second. Now we're not counting seconds anymore. We're counting microseconds, never mind milliseconds. The response time on this data is extremely important. Some of these opportunities, especially in the FX business, some of the opportunities last only milliseconds. You can trade currencies thousands of times in a single second and profit significantly if you know what you're doing. If you have the right math in place, you can profit significantly. That's what we do, is we analyze this data as fast as possible. We try to aggregate it as fast as possible, get it into our grid, and make an intelligent decision. That's what algo is. When you hear about companies talk about algorithmic trading, that's what they're talking about. It's the ability to take huge amounts of rapidly changing data and analyze them as fast as possible. Now, this is a challenge for environments like grids, because Amdahl's law states that the value of parallelizing a job is directly related to how static the data is. If the data changes, all the other servers in that parallelized job have to stop and start over again. So it's kind of a catch-22. Process it, but process it with millisecond response time. Because if the data changes before you're done processing it, then you have to start over again. And you didn't actually make any decisions, and you're out. So we're going to do things like, if, for example, the market data source sending us the information has excessive latency on the feed, we're going to do things like turn off the algo engine because we can't trust the information anymore. If the information's stale, you don't want to make a purchase decision on it. That's what a real-time infrastructure is. It's the ability to take amazing amounts of data in as fast as possible, analyze it, and make a decision. And we do this for algo engines, and we do this for trader desktops for our humans on the trading floor who have to do things like calculate the net present value and the default to zero probability of the books that they're trading. And I throw up there, Little's Law. Little's Law, one of my favorite laws. Little's Law and Worth's Law are my two other favorite laws. Moore's Law is relatively interesting, but Little's Law is interesting because that tells you that the number of transactions or people or things in the queue equals the arrival rate, how fast they get to the queue, and the time it takes you to process that transaction. This applies for how long the line is at the grocery store and applies for how long the line is inside the queuing system that's executing transactions or the analytical system that's waiting to execute transactions or analyze transactions for a trader. So you have to take into consideration how fast is it coming and how long does it take to process it once it gets there. That's how big your wait is. The other law, I mentioned Wirth's law. This is a funny one. The Wirth's law states that computers are getting, or software is getting slower faster than computers are getting faster. That's where Papadopoulos was going when he said companies are redshift companies. You know, these are certain types of companies are redshift companies where the software that they wrote requires more than what the computers can give them. That's redshifting. Wirth's law. So traditional versus SOI. Why do we do this? Yes, there is efficiency. But like I said in the beginning, the top priority is time to market and providing value to your business or your organization. That's what IT is for. And I always say that if you deploy a technology solution, but the business process doesn't actually change, then you've failed. You have to actually transform a business process to make it more profitable for the business to do what they were trying to do than they could do before without that technology. So things like algorithmic trading, executing hundreds of transactions in the span of a second, that's value. Humans cannot do that work. So that's what IT is doing for the business, is providing value. Secondarily, virtualization will take you away from doing things like bunnies populating in the data center, eating up all your power and cooling and floor space, to consolidating environment and provisioning resources on demand. Another technology I'm a big fan of right now is the Azul appliance. This is a Java coprocessor, huge amounts of processing and storage in an 11U rack space. 11U's of, I think it's some ungodly amount of processors, 796 processors and about 3/4 of a terabyte of memory and 11U's of space. We do things like run JVMs on those Azul appliances, and you get essentially pauseless garbage collection time. One of the big challenges with Java, and one of the latency issues that we have with Java and JVMs, is it has to clean up its memory space. All of those processors make it very fast to clean up that memory space. And they say that, let's take a 5 GB heap. It might take you traditionally on a multi-way, 4-way, 8-way server, it could take you as long as 5 seconds to 60 seconds to do that garbage collection step, which means everything running on that JVM has paused until the GC finishes. So we do things like run our JBoss and WebLogic containers on low-end commodity blades, and we tap into things like Azul to get our additional capacity on demand. So as it needs to ramp up from 4 CPUs to 8 CPUs to 20 CPUs to 100 CPUs, from 10 gigs to 20 gigs to 100 gigs, you just carve out the space you need, allocate it, restart. Eventually it'll get to the point where you can restart or you can allocate without having to restart. Execution is all about monitoring, measuring, optimizing, provisioning, and activating your resources and doing it all over again and never stopping. That's transit-stasis. Feedback, adapt, constant change, that's the only constant. Technology is changing at an amazing clip. Intel released a dual-core Woodcrest, then they released a quad-core Clovertown. Now they got quad CPU quad cores on machines, and Sun's out there doing T2s that have 8 cores per chip and 8 threads per core, essentially a 64-way machine in a single chip. We want to take advantage of these technologies, roll them into the environment as fast as possible in order to meet our business's needs. But we can't do that without some kind of process in place to prevent from having to wait till Saturday and do a maintenance window change. It's not sustainable. We need to get to a point where infrastructure changes can happen without impacting the continuity of the business. Where are we going next year? Next year is differentiation for Wachovia. We're going to leverage the assets that we've invested in. We're going to take share away from our competitors through time to market and our efficiency and our speed. And we're going to continue to do what we're doing. We're not done yet. There's plenty of code across the bank that we can expose and leverage as services. So look for, in your organization, you don't have to start from scratch. Take advantage of all the logic that's hardened and tested, even kicks on a mainframe. Wrap those jobs or those workloads and web services and expose them with security policies. Use an ESB gateway. Explore things like XSLT to transform the data payload to be in the exact format it needs to be to run on that web service. That's all I had. I've got about 50 seconds left for questions, so if you have a question, go ahead. Should be a microphone around here, so if we could just get a microphone handed to the hands.
What's OER stand for?
That's operational efficiency ratio. That's the amount of money we spend on technology versus the value it provides.
Hi, thanks. So with all this diversity and the interest in having trusted, reusable components, can you describe a little bit how you go through operational readiness so you can harden all of this, diversity and new technology? It just seems
great. That's a great question. We spend a lot of time on making things production ready. We've got an innovation factory lab. My team does most of their work not in the data center, but in an infrastructure, what we call an innovation factory. So we innovate in this private network, in this private environment, and we instrument all of the things that we build with monitoring tools. Then we move everything into a load testing environment, another private environment where we have load generators like Ixia on private switches, where we make sure that this thing can scale up. And in an Ixia device, that's pretty cool technology. They can simulate about 750,000 concurrent users with generating one single appliance. We also use things like Load Runner, but you definitely have to have a quality control process in place that when you're building something that is going to be shared across many business lines, that it is resilient, it is performant, it is scalable, it is secure. And I use the term ICAPS to remember what are the attributes that I'm looking for. Does it integrate? I. Does it have the capacity that you need? C. Is it highly available? A. Is it highly performant? P. And S, is it secure? ICAPS. So test for ICAPS, and then you'll have something that's manageable. So you can't just say, is it manageable? How easy does it integrate? Does it scale? What are its capacity limitations? How does it do high availability? How does it perform under stress? Where does it break? What's the hockey stick curve? Everything has a hockey stick. That's the point at which you can't add any more users. The response time eventually gets flat, or the number of users gets flat before the response time increases. And so the x-axis is response time, the y-axis is number of concurrent users. Find out what your hockey stick is before things start to pan out and you can't add any more users. That's all I have. Thank you for your time.